Hi everyone, welcome to Om Learning Lab. In this video, we are going to solve the puzzle Trials Until First Success. This puzzle has been taken directly from the book 50 Challenging Problems in Probability by Frederick Mosteller. Now this problem is quite famous in nature and has been asked in various interviews, be it for software engineering roles or quant roles. This problem builds heavily upon the concept of probabilistic expectation and random variables. So I would recommend people to watch the video on random variables and probabilistic expectations before continuing with this solution. I have attached the link to that particular video in the description of this video. Without any further ado, let's get into it. So the problem states, on average, it's just a single line problem. On average, how many times must a die be thrown until one gets a 6? Now we know what a dice is. So this is a dice and it has 6 possible outcomes. So the outcomes that are possible when you throw a dice are 1, 2, 3, 4, 5 and 6. And the problem is fairly simple. That is, on average, how many times we need to throw a dice before we get a 6. Now, although the problem is one-liner, it is kind of vague in nature, or we can say it is kind of open-ended in nature. Being able to think where exactly we are going to start solving this problem is a challenge in itself. Because we don't have any other data other than knowing the universal fact that a dice has 6 possible outcomes and each possible outcome has a uniform probability of 1 by 6. That's it. That's all we know. Now, in situations where we are asked to compute something on average, like you can see on average how many times we need to throw a dice so that you get something, when we're expected to calculate a mean value, an average, without data points being given to us directly, and on top of it, what do we already have? We just have the probabilities and we're supposed to calculate an average that directly hints us or points us rather to the direction of probabilistic expectations. So it is in situations like these, as I had mentioned in the video on random variables and expectations, that the idea of expected value becomes really important. Where you don't have data points, all we have are probability values. So, this problem needs to be solved using the concept of expectations. Okay? But how are you going to do it? The first thing that we need to do is we need to define the event. So, what the event is? The event is throwing a dice. So, let's be very thorough on this. How are you going to solve this problem? So, I will define the event here. So, what my event is? My event is throwing a dice. This is my event. Event is I'm just throwing a dice. That's all I'm doing. Throwing a die. This is the event. What are the possible outcomes? So, we know the possible outcomes are just 6, as I mentioned above, 1, 2, 3, 4, 5 and 6, and all of them have uniform possibility, which is 1 by 6. That is, if we have an unbiased die, then every output has an equal possibility, right? Just like an unbiased coin has possibility of half for each head and tail respectively. So this is my event and these are my outcomes. Now, what do I need to calculate? That basically becomes my random variable. So I need to calculate how many times do I need to throw a dice. So the event is throwing a die. These are the possible outcomes. And what I need to calculate in the end is how many times do I throw the dice? How many times does the event happen? So number of times event happens. That is what I need to compute. I mean, how many times do I need to throw a die before I get a 6? That's what I need to compute. So if I want to compute on average how many times this thing happens, how many times the event of throwing a die happens, then my random variable will take that particular value. That is, my random variable x will denote how many times do I need to throw a die. So, how I can define my random variable x? So here, the random variable x, I'll just denote random variable by rb. This will denote the same thing, number of times I need to throw a die to get a 6. Let me just write it again, just for clarity's sake. So random variable x will represent number of times we need to throw the die, which is, in other words, the number of times the event of throwing the die happens, but the condition is to get a 6. Okay, to get a 6. That's it. So I have defined my random variable to be the number of times I throw the die so that I can get a 6. Now, what else do I need to do? We know that the formula of probabilistic expectations is, so expected value or the probabilistic mean of x, expected value of a random variable, is summation of xi multiplied with probability that random variable takes the value of xi for I from 1 to n, where n is all possible outcomes in the event space. Here, what do we have to do? Here, what can x be? Here, it's very important to note that the possibilities of x, the limitation on x doesn't exist. I mean, x can be anything. Y, it can be anything. So let me write x here, and let me write probability that my, in fact, let's change this a bit. Let's write this xi. Xi is the value, the number of times that we need to throw the die to get a 6, the distinct values that are possible. And here, what is the probability that a random variable will take that particular value? I mean, in the end, we need to compute this table, right? And then apply this particular formula. Okay. So the idea is, the important observation is, there is no limitation on x. Why? Because I can get a 6 in just a single throw. I mean, if this is my first throw and I get a 6 to begin with, that's it. I mean, I am done, right? That's it. That is a possibility. And the probability of that happening is 1 by 6, which is same as the probability of getting a 6. Now, xi can be 2 as well. If it is 2, that means that in the first try, I did not get a 6. So what is the probability of not getting a 6? Probability that, let's not confuse the notations. Let me just keep it very simple. So what is the probability that I am not getting a 6? It means it can be anything from 1 to 5. I mean, it's basically 1, 2, 3, or 4, or 5. So there are 5 possibilities. So in the first throw, I did not get a 6. But in the second throw, I am getting a 6. Because here xi is 2. So the probability would be 5 by 6 multiplied with 1 by 6. Because these are independent events, yet they occur one after other. So we multiply them. So 5 by 6 multiplied with 1 by 6. I mean, these are AND events. We didn't get a 6 in the first throw, and we got a 6 in the second throw. Hence the multiplication. So xi can be 2 also. Like, we can get a 6 in 2 throws. Similarly, we can get it in 3 throws also. For 3 throws, in the first throw, we should not get a 6. The possibility is 5 by 6. Similarly, and in the second throw also, we should not get a 6, whose possibility is again 5 by 6. And in the third throw, we should get a 6, whose possibility is 1 by 6. And so on and so forth. So if we see the total number of possible values of capital X or a random variable, that is the number of times we need to throw the die to get a 6, there is no limitation on that. It can go up to infinity. I mean, it can take any value, right? and for every value we'll have this pattern. So if xi is some n, we'll have 5 by 6 to the power n minus 1 multiplied with 1 by 6. That's something that is important to know. I mean, if we're getting a 6 in n throws, it means we did not get a 6 in the first n minus 1 throws. If we did not get a 6 in the first n minus 1 throws, the probability of that happening is 5 by 6 raised to the power n minus 1. I mean, it will be 5 by 6 into 5 by 6 into 5 by 6 n minus 1 times for all those events occurring independently. And for the final throw or the nth throw, we must get a 6 whose probability is 1 by 6. And all these are AND events. They occur, this event occurs and that event occurs, so on and so forth, so they are multiplied. So this is the for, and our random variable can take any number of values from 1 to infinity. Now here is when the problem turns from a problem of probabilistic expectation into a problem of number series. I mean, that's the beauty of mathematics. You just never know how a problem is going to transform itself from one form to another. Because once I have observed this much, that is how my random variable behaves, for each particular value the random variable is going to take, what is the probability and what is the total number of possibilities for the random variable, that is infinity in this case. Once I have noted this much, I need to go back to the standard formula of expectations and I need to apply it. When I do apply it, what do I get? What I'll get is something very interesting. So expected value for this E of x, expected value of x, or the probabilistic mean of x, or the probabilistic mean for the number of times we need to throw a die to get 6. That's what we want, right? I'm just, playing with words here. On average, how many times you need to throw a die to get a 6? That's what we are doing here. Expected value of x, probabilistic mean of x. Probabilistic mean, or on average, how many times we need to throw the die to get a 6. I'm just putting everything together so that people don't get lost. I mean, we are not doing something out of the box. That's literally just out of the standard definition. So, what will E of x be? E of x will be application of the standard formula, summation of every xi, that is the random variable, the value that a random variable can take, multiplied with the probability that random variable takes that value, which is for I, usually it's for I equals to 1 to n, where n is the total number of possibilities for the random variable. But here it's infinity, as we noted. It can be anything. Let me put the values. So for x is equal to 1, it will be 1 multiplied with 1 by 6. For x equals to 2, it will be 2 multiplied with 5 by 6 multiplied with 1 by 6, plus for x equals to 3, it will be 3 times 5 by 6 square multiplied with 1 by 6, plus similarly for 4 times, it would be 4 multiplied with 5 by 6 whole cube, because for the first 3 chances, we did not get a 6. We are not getting a 6, and we are not getting a 6, and we are not getting a 6. So 5 by 6 multiplied 3 times. And finally, in the 4th trial, we got a 6. And similarly, so on and so forth. This is an infinite summation series. And in many ways, it is something that is known as AGP. In fact, yeah, it is an AGP. So in geometric progression, we just have powers multiplied. In arithmetic progression, we have values added. So geometric progressions usually have the form A, AR square, so on and so forth. Like R is being multiplied here. And in AP, arithmetic progression, we have A plus D, A plus 2D, so on and so forth. It's a combination of both, because here this 1 becomes 2, 2 becomes 3. Like this particular value keeps on increasing by 1. Whereas there is a R value involved as well. Like 5 by 6 is being multiplied. So I am not going to get into the exact mathematical rigor and the definitions as to whether this fits into the definition of a AGP or not. Because in the end, what we should know is how to solve such kinds of series. So now the problem has translated itself into being able to solve this particular series. How do we do that? The first thing that I am going to do is something that should come to everybody's mind. We just take 1 by 6 common. When you take 1 by 6 common, you get 1 plus 2 times 5 by 6 plus 3 times 5 by 6 square plus 4 times 5 by 6 cube, so on and so forth. The next thing that I'm going to do is replace 5 by 6 with r. This just looks, writing 5 by 6 too many times when I'm trying to simplify and find a pattern that just too cumbersome. It's a general practice in mathematics to represent them with variables. So let r represent 5 by 6. If that is so, then what I'm supposed to calculate now is 1 by 6 common. 1 plus 2 times r plus 3 times r square plus 4 times r cube, so on and so forth. Now for a brief moment here, let's try to think about how do we compute this particular summation. Let me write it here separately. Let me represent that with s, which is 1 plus 2r plus 3r square plus 4r cube plus so on and so forth. How do I break this? How do I find a pattern out of this? What should come to my mind is, what should come to anybody's mind, in fact, it's a standard trick, is try to break down the series, any numerical series that you get, into known series, known results. The known result that should be visible from here is, from this 2r, I can just take 1r, 1 plus r. From this 3r, I can take 1r square. From this 4r cube, I can take 1r cube, so on and so forth. Like the next term would be 5 times r to the power 4. So I would also take 1 r to the power 4 out of it, so on and so forth. That would be one part. Plus, what remains? From 2r I took 1r, so 1r is left. From 3r square I took 1r square, so 2r squares are left. Similarly, 3r cubes would be left, so on and so forth. This is what is left. This is called breaking summations, finding residues. And that is a really helpful technique in many ways. How? Because for starters, we know what this summation is going to be. It's an infinite GP, 1 plus r square up to infinity. We know the summation to be 1 by 1 minus r. This will be the summation for the first part. And as to the second part, as it usually happens in mathematics, when you start simplifying and breaking series or terms into known patterns, other new patterns, other helpful patterns begin to emerge. What emerges here is, if you take r common here, you will get what? 1 plus 2r plus 3r square plus 4r cube, so on and so forth. Right? What is this? Have we seen this before? Isn't this s? Yes, it is s. So I can replace this with 1 upon 1 minus r plus r common s. Now, simplifying the equation, taking all terms of s on one side, I'll get s common 1 minus r is 1 by 1 minus r. That means s becomes 1 divided by 1 minus r whole square. So I literally just derived a common solution, a common form solution for any geometric series or AGP or whatever it is, which has the form like this: 1 plus 2r plus 3r square plus 4r cube. If you have a series like this up to infinite terms, this is going to be the final outcome. Why? Because you break it into two parts. One is the known, one is the unknown. You know the result for the known part, and in the unknown part, when you are taking r common, you are seeing a known pattern, which is s. So you plug that back into the equation and you get the final result. Now, one more side quest that I would like to do before I jump back to the original solution, original problem, and people may feel free to skip this, is that I would still like to show people from where this result came from. Like the infinite summation of 1 plus r square plus r cube up to infinity is 1 by 1 minus r. I don't want people to assume this. This is easily derivable. This is not some out-of-the-box solution that we can't derive. In fact, we can derive this just as easily. So this is a side quest that I'm doing. Please feel free to skip and go to the next section, which is coming back to the solution, putting back this value in the original summation problem that we're dealing with. So people can feel free to do so. Meanwhile, let me just solve this real quickly. Let's define S dash as 1 plus R square plus up to, what can we do? Let's say we have, we can derive for n terms maybe. Let's say we have till r to the power n minus 1. Let's say this is the first summation term that we have. And we can also write S dash as, this is called shifting method. Most people might be aware of it. So here I'll write the same thing, 1 plus r square, so on and so forth. But here, since I have shifted terms by 1, here what am I going to get? So for this corresponding position, I'll get r to the power n minus 2 plus r to the power n minus 1. That's what I'm going to get. And if I take a subtraction, 0 becomes 1 plus, you see r minus 1 here, you combine this. And here r square minus r. So r square minus r will be, if you take r common, it will be r minus 1. So plus r common, r minus 1. Similarly, in the next part, you would have r cube minus r square. So you take r square common, it will again be r square times r minus 1 plus so on and so forth. For these two particular terms, you can take, r to the power n minus 2 common, and you get r minus 1, and you get a minus r to the power n minus 1, right? I just explained what happened here a little bit more. So what I did was, S dash is what I'm trying to compute, which is 1 plus r square up to r to the power n minus 1. Let's say I'm computing for n terms, let's say. Now, I'm writing the same S dash, but I'm shifting the terms by 1. Once I write it in that form, I take a subtraction. So S dash minus S dash is 0. 1 minus, here this is effectively 0, so it is 1. I'll combine these terms, r minus 1. And I'll combine these two terms, r square minus r. And I'll combine the next two terms. So here it would be r cube, right? So r cube minus r square. You take r square common, it is r minus 1 again. And so on and so forth, till the last term. So you take r to the power n minus 2 common, you still get r minus 1. And finally, you are subtracting this term, this from this. So you'll get a negative here, minus r to the power n minus 1 here. Fair enough. We can simplify this. So 0 equals to, what can we do? We can bring r to the power n minus 1 to left side and 1 to the left side as well. So r to the power n minus 1 minus 1 is same as r minus 1, you take common. What will be left with is 1 plus r square, so on and so forth, till r to the power n minus 2. This is what you are left with. Okay. Now, this pattern again should look familiar. It should look familiar because this is sum up to n minus 1 terms. In other words, r to the power n minus 1 divided by r minus 1 is same as 1 plus r square up to r to the power n minus 2, or sum of n minus 1 terms. So to compute the original sum, which is still r minus n minus 1, r to the power n minus 1, we can simply replace n minus 2 with n minus 1 here, or in other words, n becomes n plus 1, in which case the solution would be r to the power n minus 1 divided by r minus 1. This is the GP summation for n terms. Fair enough. Now, what happens when this becomes infinity? So, the original sum till n terms S dash turns out to be, let me write it in this way, 1 minus r to the power n divided by 1 minus r is the same thing. So, what I'm interested in finding out is limit n tends to infinity 1 minus r to the power n divided by 1 minus r. This is what we are supposed to find because we have infinite terms. That's what we are using here, right? Infinite terms, this result. So there, all we have to do is, if this is tending to infinity, and remember, this is always for r, which is less than 1. Okay? Greater than 0, less than 1. R lies within the unit circle. That is a property of progressions. If that happens, if it is a fractional value and you are tending that to infinity, it will go to 0 eventually. Even if you take a very large fraction, for example, 5 by 6, some people might wonder if this step is correct. So what will happen here is once you tend n to infinity for this will become 1 by 1 minus r. This r to the power n will become 0 if r is a fraction and n is infinite. So to prove that point, if I take this example, 5 by 6, you square it, you get 25 by 36. So this is smaller than 5 by 6 if you think fraction-wise, fractional value-wise. You take another power, it will become even smaller. So after another power, what will I get? 5 cube, 125 divided by 6 cube. 6 cube is what? 360, 396, is it? 36 into 6. 36. It's 260. Yeah, it's even smaller. And it will keep on going smaller. So if you have infinite number of terms, it will eventually become same as 0. Thus giving us this result. So this is how we can derive the formula for infinite number of terms GP. That's not an out-of-the-box form or out-of-the-box solution, which is not easy to derive. It's quite easy to derive as I showed. Now, coming back to the original problem at hand, once we have this formula, we just need to plug this back here. So the expected value that we are looking out for is same as 1 by 6. This is 1 by 1 minus r whole square. What is r? R is 5 by 6. Just plug that back in. So it is 1 by 6. Here 1 minus r, 1 minus 5 by 6 would be 1 by 6. 1 by 6 ka whole square is 1 by 36. 1 by 1 divided by 1 by 36. This is what we are getting. Right? Because 1 minus r is 1 by 6. 1 minus 5 by 6 is 1 by 6. And that's that squared. And since this is 1 upon 1 by 36, this goes up. Ultimately, we are left with 6. Or in other words, the e of x that we are interested in computing, that turns out to be 6. Therefore, e of x is 6. Or the expected value of x, or the probabilistic mean for x. That is the number of times we have to throw a die until we get a 6. On average, the probabilistic mean. What is the expected value? How many times on average do we have to throw the die? I'm sorry, I was going to say random variable. My bad. That's what is going on in my mind. So, on average, how many times you need to throw a die to get a 6? Turns out to be 6. That is the expected value of the random variable. What was our random variable? It was this. Number of times you need to throw the die to get a 6. So the expected value for that, the probabilistic mean for that, on average how many times we need to do that, turns out to be 6. This is the entire solution and an application of the grand idea, that is probabilistic expectations. We started off by defining what our random variable is. Then we made an observation that what all values can our random variable take. It can be 1, 2, 3, all the way up to infinity. And we define how the probabilities for each of those values would look like. Then we plug those values into the formula for calculating expected value. And we noted this particular pattern, which turned the problem or transformed the problem into a problem of series computations. Then we worked on computing this particular series value. You break it up into two parts. One is a known pattern. One is whatever is left over. You plug in the standard value for the known pattern and you hope that the rest of the part which is left shows you something similar. It does in that case. It's basically S if you take R common. You plug that back into the original equation and you get this form. Plugging that back in, you get the final expected value, or on average the number of times you have to throw a die to get 6 comes out to be 6. And on a side quest, I also showed how to compute geometric progression for infinite number of terms. This is, I don't exactly know what the name of the method is, but it's sort of a shifting method, so to speak. Just a sort of arrangement, that's it. Just a mathematical trick to be able to solve it. And then you take limits. This is just one of those applications of probabilistic expectations. That there are many similar problems as well. So I remember there is this puzzle that in a certain kingdom, couples try to make kids as long as they don't get a baby girl. So every couple tries to have kids until and unless they get a baby girl. How many times on average do they need to try to have kids to get a baby girl? So, problem on that paradigm, so to speak, on those lines. So for that problem, it's basically probability of getting a boy is half, probability of getting a girl is half. And then if a couple gets a girl on the first try, it's just half. If a couple gets a girl on the second try, it's half, because in the first try, the couple got a boy. And then in the second try, they got a girl, and so on and so forth. You can see that it almost follows a similar pattern for this particular problem. But then that's a different problem. I happen to see a similar problem on different sites. I'll not be taking names because it has appeared across different sites. But that's just another example of application of this idea. I hope you got to see the application side of expectations and random variables in this problem, and you got to understand thoroughly what or more specifically how to apply the idea and how to solve this particular puzzle, this beautiful puzzle, which is really well known. Thanks for watching this video. Like and subscribe if you like my content. I'll see you in the next one. Bye.